distribution of forces, resolving forces into the various components. Now, this example number 2, it says that the link below is subjected to two forces, F1 and F2. Determine the magnitude and the direction of the resultant force. So we are to determine the magnitude and direction of the resultant force. So from the diagram, we know the various direction of the magnitude. So how do you solve this problem? First, you have to resolve the individual forces, that is F1 and F2, into the X and Y direction. Now when you resolve F1 and F2 and you sum forces in the X, you have 600 cos 30 minus 400 sine 45, and you have the sigma Fx to be 236.8. Now when we sum forces also in the Y after resolving the forces into the X and Y components, we get 600 sine 30 plus 400 cos 45, and that one, the summation of forces in the Y direction will give us 582.8. 582.8. To find the resultant, we need to find the square root of summation of forces in the X squared plus summation of forces in the Y squared. And when you substitute into that relation as we did previously, you're going to have the resultant force to be 629 Newton. So how would we find the direction? Earlier on, I explained that if you have sigma Fx and sigma Fy, you try and plot it on the X and Y axis. Now when you do that, you have it this way, and you find the tan theta of sigma Fy over sigma Fx. Then you do a tan inverse of sigma Fy and sigma Fx, and you get your theta. So theta will be equal to 67.9 degrees. That will give you the value for theta. Now I'm going to give you an assignment. So this will be your next assignment. You are to determine the magnitude and direction of the resultant force. You are to determine the magnitude and direction of the resultant force. Go through the process, go through the step, and determine the magnitude and direction of the resultant force. Another assignment for you: 4 forces act on both as shown below. Determine the magnitude of the resultant force. We are also to determine the magnitude of the resultant force. You go through the step, you resolve each of the forces. After resolving each of the forces into the X and Y direction, you sum forces in the X together, you sum forces in the Y together to get sigma Fx and sigma Fy. Having obtained sigma Fx and sigma Fy, you use the formula Rf is equal to square root of sigma Fs squared plus sigma Fy squared. Then to obtain the direction, you use tan theta is equal to sigma Fy over sigma Fx. x, and that will help you find the theta. Simply as that. So also include this to the assignment and submit it to the Gmail platform, which is easylearningplatform@gmail.com. I'll be expecting your assignment so that I can review your performance. If you have any questions so far, get interactive with us. If you want any clarification for us to do, get interactive with us on our YouTube channel and our WhatsApp page. Get interactive with us, or better still, send us a message into the Gmail. We will review it and we'll get back to you. Now move on to the next topic, which is rectangular component of a force in space. In the previous example that we looked at, resolution of forces, we tried to resolve forces into x and y component, into its rectangular component in x and y. That was 2 dimension. But now we are going to focus on resolving forces into x, y, and z component. 3 dimension. 3 dimension. So we are now going to look at 3-dimensional coordinates. Now in the diagram, we have a rectangular box. Now we have the various direction or axis. Now this is the y axis or Cartesian plane. This is the s axis, and this is the z axis. Now there's a force F from the origin O. This is the origin O. There's a force F of magnitude F from the origin O. This theta x is the direction that the force makes with the x-axis. Theta y is the angle the force makes with the y-axis. Theta z is the angle the force makes with the z-axis. The force makes with the z-axis. Now, you are moving, the force is moving from the origin O to this point. Now, you can find the various components of the force F along the Cartesian coordinate. You can find the various components of the force F along the Cartesian coordinate. Now let me start from the origin. Now I can move from this point through on the x-axis. I get to this point. Now that gives me fx. That gives me fx. Then I move upwards on the y. That gives me fy. Then I move from this point to meet the force at this point. That gives me, so I move on the z direction. That gives me the component of it in what? The z direction. Now, if I want to find the rectangular component of the force F with the angles between the forces and axes, Fx will be equal to F cos theta x. F cos theta x. Fy will be equal to F cos theta y. Fz will be equal to F cos theta z. Now the force vector or the Cartesian vector This gives me magnitude. The fx is magnitude, fy is magnitude, fz is magnitude. Now I want to find it vectorially as a force vector. How do I convert it into a force vector? Now we have unit vectors. What are unit vectors? A unit vector is a vector whose magnitude is 1. Now when we take the three-dimensional Cartesian coordinate, okay, this is x coordinate, this is y, and this is z. Now what is a unit vector? A unit vector is a vector whose magnitude is 1. Now the unit vector in the x direction is I. The unit vector in the y direction is j. And the unit vector in the z direction is k. So a unit vector is a vector whose magnitude is 1. So now representing these forces fx, fy, and fz vectorially, that means that I must bring the unit vectors. The unit vectors tells you which direction you are in. So this is in the x direction. So it will be what? I. So I have the force vector or the Cartesian vector will be equal to fxi. It means that a magnitude of fx in the x direction. Now this formula gives us a certain expression. Now this F is the magnitude of the force, and the whole of this cos theta xi plus cos theta yj plus cos theta zk is the unit vector. So now you can have your force vector, which is Fr, to be the force, which is the magnitude of the force, times the unit vector, times the unit vector, where the unit vector lambda is equal to cos theta xi plus cos theta yj plus cos theta zk. Okay, so lambda is equal to the unit vector. What is the relationship between the angles? What is the relationship between the angles? Theta x, theta y, and theta z. Now, the relationship between the angles trigonometry is
cos square theta x plus cos square theta y plus cos square theta z equals to 1.
Example number 1. Express the force F shown in the figure below as a Cartesian vector. So we have the figure here. We have to express it as a Cartesian vector. It means that we should find the force vector. Now, what is the approach? We know theta y. We know theta z. But we don't know theta x. So we need to first find for theta x. How would you find for theta x? Now let's solve the problem. Solution. Our theta y is equal to theta y. That is 60 degrees. Theta z. What do we have? 45 degrees. Theta z, we don't know, because this is giving us what? Alpha. So our theta z is alpha. How do we find the alpha? We know the relationship between theta x, theta y, and theta z. We know that
Cos square theta x plus cos square theta y plus cos square theta z equals to 1.
So substituting the value of theta into the equation, so we have cos squared theta is equal to 1 minus into bracket 0.5 squared minus 0.707 squared. So we square both sides. So we have cos alpha is equal to square root of 1 minus 0.5 squared minus 0.707 squared. Now, what is alpha? Alpha is equal to plus cos alpha is equal to plus or minus 0.5. Cos alpha is equal to plus or minus 0.5. How do you find alpha? We find the cos inverse. So cos alpha is equal to 0.5, positive 0.5. Now alpha is equal to cos inverse of 0.5. And what do we have? We have 60 degrees being the value of alpha. Cos theta is equal to minus 0.5. So we have cos alpha is equal to negative 0.5. So cos alpha is equal to cos inverse of negative 0.5. And what do we have for alpha? We have 120 degrees. Now let's go back to the diagram. Now on this diagram, if you want to find the various rectangular components, I'm moving from the origin coming to this point. I will move along this way in the y. So y is positive. I move along this way in the x. X is also positive. Are you seeing it? Fx must be positive. But you do it at home. We discard alpha is equal to 120 and we use alpha is equal to what? 60. Because alpha equal to 120 will give us what? A negative value, which is not what we should be what? Expecting by inspection. Therefore, theta x, which is equal to alpha, is equal to 60 degrees. So now we've been able to find theta x or alpha. We've been able to find theta x or alpha to be 60 degrees. But the question says that we should find or we should express the force, the 200 force, that is the magnitude, in terms of what? The Cartesian vector. So we are finding the force vector. But from the formulas, we know that force vector is equal to the magnitude of the force into bracket cos theta xi plus cos theta yj plus cos theta zk. So substituting all the known variables into this formula, we have the force vector to be 200 into bracket cos theta x to be 60 degrees I plus cos theta y. Cos and our theta y is giving us 60 degrees j plus cos theta z. Theta z is giving us 45 degrees k. So what is our force vector? our force vector now becomes 100I plus 100J plus 141.4 kilonewtons. So we have found for the force vector. Okay, so we move on to the second example. Example number 2. We are to determine the magnitude and the coordinate direction angles of the resultant force acting on the ring in the figure below. So that is the figure below. We are to determine the magnitude and the coordinate direction angles of the resultant force acting on the ring below. Now, how do we find the vector force, the resultant vector force? From the program law, we're going to sum the forces because the forces have been given to us vectorially. So it's very easy. We're going to add F1 and F2. Adding them, we have 60J plus 80K Newton plus 50I minus 100J plus 100K Newton. When you add them according to the axis, you put I together, J together, K together. So you have 50I minus 40J plus 180K Newton. This is Newton. Now let's find the magnitude. How do you find for the magnitude? Now to find the magnitude of the resultant force FR is equal to square root of 50 squared plus minus 40 squared plus 180 squared. It's very simple. Equals to 191.0 Newton. The coordinate direction angle alpha, beta, lambda are determined from the component of the unit vector acting in the direction of FR. We know that if you want to find the force vector is equal to the magnitude of the force times lambda, and lambda is the unit vector. But now we know this, we know that we want to find this, so we divide this one by F, we divide it by F, so the unit vector lambda is equal to the force vector over the magnitude. So that is what has been done here. And we know that lambda, which is the unit vector, is equal to cos theta x I plus cos theta yj plus cos theta zk. So that has been done. That's what has been done. So we're going to make FR, which is the force vector over the magnitude. Then we compare both sides. Then we can find our angles. So now back to the solution. Our unit vector FR is equal to the force vector over the magnitude of it, which is equal to 50 over 191.0I minus 40 over 191.0J plus 180 over 191.0K. That will give us 0.2617I minus 0.2094J plus 0.9422K. So now we compare both sides of the equation. Now comparing this, we have that cos theta Now this theta is the same as theta x. And this is the same as theta y, and this theta z. Theta z. So when you do that, your theta x will be equal to 74.8 degrees. Your theta y, 102 degrees. And theta z will give you 19.6 degrees. So assignment on this problem: two forces act on a hook shown. Specify the magnitude of F2 and its coordinate direction angles so that the resultant force Fr acts along the positive y-axis and has a magnitude of 800 Newton. So that is the diagram there. Again, endeavor to solve it, attempt to solve it. Once again, after you are done, make sure you send your solution to the Gmail of this platform, that is easylearningplatform@gmail.com, so that we can access you and have a look at your performance. Another example for you to also work on. I will show the solutions, but I won't solve it. Next, we go to rectangular component of the force F defined by the location of 2 points, position vectors. Now, in this approach, you are to determine the position vector of the force. The position vector of the force. And at the end of this review, you should be able to know how to find position vectors. Okay, how to find position vectors. Because if you want to find the force vector in a scenario like this, the force vector F is giving us the magnitude of the force times the unit vector. Now, what is the unit vector? Unit vector is equal to position vector over magnitude of the position vector. Unit vector is equal to position vector over magnitude of the position vector. So you know that in this formula, you should find your position vector and you should know how to find the magnitude of the position vector. Now, in this example, what will be our position vector? Our position vector. Now, the force is moving towards this direction. Now, this is the origin of the force. So, from the origin of the force, where the force is starting, you are going to move along the Cartesian coordinate to locate the force here at B. So you are going to move from A along the Cartesian coordinate to B. So I will move this way. You can move in any direction along the Cartesian. is correct. So I want to move from this side to this side. Okay? To this side. So I move dx in the x direction because this is x along the x. So I have dxi. And it's positive whenever you are moving away from 0, 0. Okay? Whenever you are moving towards the x-axis, this way is positive. If you move towards this way to this point, it becomes negative. Okay? So it's positive dxi. Plus, I'm going to move, so I'm at this point. I'm going to move upwards in the y. That is positive. So plus dyj. So I am at this point, then I move in this direction. I move in this direction. What is happening? I'm moving in the z direction. Are you seeing it? I'm moving in the z direction, but this time I'm not moving away from the origin of the coordinate, but I'm moving towards it, this direction. Okay? So that means that I'm going to have what? Minus dz k. So that will give me my position vector. So how would you find for the magnitude of the position vector? How would you find for the magnitude of the position vector? This is the position vector. So I'm going to find the magnitude of the position okay, so you are going to have the square root of dx squared plus dy squared plus dz squared. And this will give you the magnitude of the position vector. The magnitude of the position vector. So to find the unit vector, we have the position vector, which is dxi plus dyj minus dzk all over the magnitude of the position vector, which is square root of dx squared plus dy squared plus dz squared. And this will give us the unit vector. So having found the unit vector, let D represent the magnitude of the position vector, which is square root of dx squared plus dy squared plus dz squared. So then we can have the unit vector being simplified. The unit vector being simplified as dxi plus dyj plus this minus dzk all over d. So simplifying this equation, I have dxi over d plus dyj over d minus dzk over d. So to find the force vector F, which is equal to the magnitude times the unit vector. So I have my magnitude, which is F from this F. So I have F multiplied by dxi over d plus dyj over d minus dz over d times k. And this will give me the force vector or the Cartesian. Example 4. Example 4. We're going to now apply how to find the force vector using the positional vector approach. The hinge plate is supported by a cord AB. If the force in the cord is 340 Newton, express this force directed from A to B as a Cartesian vector. We have to express the force from A to B as a Cartesian vector. What do we have? Solution. We know the magnitude of the force to be 340 Newton. So the magnitude of the force is 340 Newton. That is the only known variable. We also know the various distance from the origin of the force to the Cartesians. To the Cartesian. Now we have to find the Cartesian vector. But we know that the Cartesian vector, force vector, is equal to what? The magnitude of the force times the unit vector. Do we know our magnitude? Yes. And our magnitude is 340 Newton. Do we know unit vector? No. We have to find for the unit vectors. What is the unit vector? From the previous lesson, we realized that what? Unit vector is equal to what? Position vector over what? The magnitude of the position vector. So we need to find for the position vector. In our figure given below, what will be the position vector? Now you are going to move. Now the force is moving from A to B. That is the direction of the force. So now you are going to move from A along the Cartesian to B. And that will give you your position vector. So now let's do it together. I am moving from A. So I move from A to this point. Okay? Now, you know, this coordinate is going this way. But now I am moving this direction, which is opposite to this. So I'm going to have what? Negative. Okay? So this is the actual direction of the coordinate. But now I am moving this way, which is what? Negative x. Negative 8. So I have negative 8 in which direction? In the x direction. And the unit vector in the x direction is I. Then I move from this point to this point along the Cartesian in the y. And what is the magnitude here? Is what? 9 meters. 9 meters. Is it negative or positive? The direction of y is this way, but I'm moving in the opposite direction, so I have what? Negative. Negative 9j. J is the unit vector in the y direction. Then I move from this point upwards to B. That will be 12. The unit is 12. So, and it's moving upward. We are moving upward. And it's also in the same direction as the Z. So I have plus 12k. And that gives me the
position vector.
Having found
The position vector.
what will be my magnitude. So let me call magnitude, let me write it as D. The magnitude of the position vector as D. And we know that it's the square root of all this. So 8 squared plus 9 squared plus 12 squared. The reason why I'm not bothered about the negative is that whenever you square a negative number, you get what? A positive value. So that is why. And we'll have this value to be 17. To be 17. So the magnitude of the position vector is 17. So how would you find the unit vector? So your unit vector will now be, before we found for the position vector, before we found for the magnitude, so we just go to what? Substitute. We're going to do substitution and put those obtained value into the equation. So we have minus 8i minus 9j plus 12k all over 17. So we are going to have minus 8 over 17i minus 9 over 17j plus 12 over 17k. And that will be the unit vectors. Now, what will be our Cartesian vector? It's what the magnitude times unit vector. What is our magnitude? 340 Newton. 340 Newton is our magnitude. So we have 340 multiplied by the unit vector minus 8 over 17i minus 9 over 17j plus 12 over 17k. So now, what do we get for the Cartesian vector? So you're going to multiply 340 by negative 8 over 17. Then when we finish, we add the I. So we have minus 160i. Then we do the same thing. We have minus 180j. And we do the same thing for the k. And we have plus 240k. Now, this gives us the vector force. The vector force. So your assignment, the roof is supported by cables as shown in the photo. If the cable's exact forces FAB equals to 100 Newton and FAC equals to 120 Newton on the wall hook at A as shown in the figure below, determine the resultant force acting at A. Express the result as a Cartesian vector. So you go through the problem, go through the solution, go through the steps, you'll be able to solve this problem. Again, after you are done, kindly send your solved problem to the Gmail account easylearningplatform@gmail.com so that we can review and assess your performance and understanding of the lesson. So we continue from where we ended the last time. We'll continue with equilibrium of a particle. Equilibrium of a particle. Now, what is equilibrium of a particle? A particle is said to be in equilibrium if it remains at rest, if originally at rest, or has a constant velocity if originally in motion. For equilibrium to be maintained, Newton's first law of motion must be satisfied. So if you want to maintain equilibrium, Newton's first law of motion must be satisfied. Now, what is a particle? In our previous lesson, we said that a particle is a portion of matter so small that is considered as a geometric point. Remember, we said that a particle has mass but no size. Now, we are looking at equilibrium of a particle. When we go further into the course, we will do equilibrium of rigid body. But at this point, you are looking at equilibrium of a particle. What is equilibrium? You are saying that a particle is in equilibrium. That means that a particle which is at rest will continuously be at rest. It will not move. If the particle is in equilibrium, there will be no movement in the particle. This laptop is at rest. That means that I'm not expecting it to move from this position. It has to be there. It has to be in equilibrium. If we want to maintain equilibrium, ensure that the forces are balanced. The forces acting on the particle is balanced. So there is no movement within the particle. We are saying that then the sum of forces acting on the particle should be equal to 0. So we have summation of forces should be equal to what? 0. The resultant forces acting on the particle must be 0. The resultant force acting on the particle must be 0. Where sigma f is the vector sum of all forces acting on the particle, thus all the forces acting in all directions must sum up to 0. Example, that is sigma fx should be equal to 0, sigma fy should be equal to 0, and sigma fz should be equal to 0. These equations are known as what? The equations of equilibrium. So the concept of equilibrium is very important. Okay, it means that if you have a particle this way and you have a force F1 acting on it and you have another force F2 acting on the particle, for this particle to be in equilibrium, then F2 must be equal to what? F1. So that the resultant force will be equal to what? 0. Okay, so that the resultant force will be equal to what? 0. Then you can say that the particle is in equilibrium. So we move on to the first example on equilibrium of a particle. How to apply the equilibrium equations. Remember that for the equilibrium equation, we have summation of forces in the x direction is equal to 0, summation of forces in the y direction is equal to 0, summation of forces in the z direction is equal to 0, provided it's a 3-dimensional Cartesian coordinate. If you are dealing with only 2D, x and y, its summation of forces in the x direction must be equal to 0, summation of forces in the y direction must be equal to what? 0, which is a 2D. Now this is a simple 2-dimensional analysis, x and y. So we're going to see how to apply the equilibrium equation. Two cables AC and BC are joined together as C. and a load of 2,000 Newton is applied, as shown. Determine the tensions in the cables. So how do we solve this problem? We've been solving problems on forces resolution. So this one, we're going to apply resolution of forces. Then the new thing that we're going to do is that we're just going to apply the equilibrium equations. So it's very simple. We have to find the forces in the various Cartesian coordinates, the y component and the x component. When we finish, we sum the forces in the x component together, then we equate it to 0. We sum the forces in the y component together, we also equate it to 0. Okay, so we have to first resolve this force. Okay, there are various ways to do that. Now, so this is a simple free body diagram. This is a simple free body diagram. Free body diagram is an outline sketch of a body which is completely isolated from the surrounding. Then you consider the forces which are acting on it. We'll look at it in the coming lessons. So this is the tension. We are trying to find the tension in the cable. So this is a cable. This is also a cable. AC is a cable. BC is a cable. So we're trying to find that tension which exists in the cable. So we call that tensional force FAC. There's also going to be tension in cable CB. We call this FCB. So FCB is an unknown force. That's the tension we are trying to find. They are unknowns. Then the next step is to resolve, because this force is not in the x nor the y. Because we're going to sum forces in the x direction, sum forces in the y direction. It then supposes that we have to what? Resolve this in the x and y component. And in doing that, there are various ways of doing that. This angle will also be 30. You know that already. Our direction is upward. The direction of FAC is upward. So remember, I told you that the direction is very important. So you move along this point to A. So you move this way and that way. Then we have, this is opposite side. So we have FAC sine 30. And we have FAC cos 30. Then, having found for the rectangular component of FAC at an angle of 30 degrees from the horizontal, we also find the force FAC in terms of what? The rectangular component. So the same thing, you complete your right angle, triangle, then your forces. So this time round, the force is moving from C to B. It's moving from C to B. That's the direction of the force. It means that I have to move from C along the Cartesian plane toward B. So I move from C to this direction and to that direction. Then I have this, the angle here is the same, Z. So this angle is what? 45 degrees. Then this side becomes our what? Opposite side. So we have FCB sine 45 degrees. And we have FCB cos 45 degrees. So now we've been able to resolve all the forces into components. We've resolved force FAC into the rectangular component. We've been able to resolve FCB into the rectangular component. That is good. What next? Now we apply the equilibrium condition. Apply the condition. We apply the equilibrium conditions. What are the equilibrium conditions? Sum of forces in the x direction should be equal to 0. And sum of forces in the y direction should be equal to what? 0. Two equilibrium conditions are going to be applied. So we have sigma fx should be equal to 0. What are the forces in the x direction? The forces in the x direction, we have FAC cos 30. Now we have intended our direction for the x to be this way. You know, this is an arbitrary direction. You have to choose your direction. I prefer to move this way as positive. I prefer to make the direction going to the right as positive, okay, and the direction coming to the left as negative. I prefer it. Somebody can also use the direction going to the left as positive and the direction going to the right as negative, but you have to maintain consistency. So sum of forces moving in the x direction should be equal to 0. Then we have FAS cos 30. Now this cos 30 is moving in this direction, which is opposite to our intended direction. So we have negative FAC cos 30. Negative FAC cos 30. Then this is also in the x. It's moving in the positive direction. We have plus FCD cos 45 degrees. Is that all for the x? I think there's no other forces in the x direction. So we sum it equal to 0. We said that for a particle to be in equilibrium, the resultant force must be equal to 0. So there will be no unbalanced forces to unbalance it and cause it to move. So we have, what is cos 30? Cos 30 will give us minus, so we have minus 0.8660 FAC plus 0.7071 FCD should be equal to 0, equation 1. So the next equation we apply is the sigma Fy should be equal to 0. So sigma Fy, this direction is positive, should be equal to 0. So from the diagram, which of the forces are moving in the y? Which of the forces are moving in the y? I can see FAC sine 30 and I can see FCD sine 45 and I can also see 2000 Newton down here. So what I have is that I have FAC sine 30 is moving upwards, okay, the same as our direction, so it's positive. So we have FAC sine 30. Then we have plus, also positive, moving upwards, FCD sine 45 degrees. Okay, don't forget, this is also coming downwards in the y, and this is moving downwards, opposite to our direction. It becomes negative 2000 Newton. Should be equal to what? 0. Should be equal to 0. So what do we have? What is sine 30? We have 0.5 FAC plus 0.7071 FCD should be equal to 2000. Equation 2. So we have equation 1 and equation 2. So solving equation 1 and equation 2 simultaneously. We solve them simultaneously. So solving them simultaneously, we have FAC to be 1464.12 Newton. Then CB will be 1,793 Newton. So solve it. Solve equation 1 and equation 2 simultaneously, and you arrive at this answer. Okay. Assignment number 1. Determine the tensions in cable BA and BC necessary to support the 60 kilogram cylinder D. You are also to solve this. A sailor is being rescued using a boat swan's chair that is suspended from a pulley that can roll freely on the support cable ACB and is pulled at a constant speed by cable CD. Knowing that alpha is equal to 30 degrees and beta is equal to 10 degrees, and that the combined weight of the boatswain's chair and the sailors is 900 Newton. Determine the tension in A, the support cable ACB. B, the traction cable CD.